Well, this is the 26th annual Christmas lecture, and for 20 years we call it the Christmas tree lecture. The idea was that well, trees is one of the most important things to computer scientists, and every year I learned at least two new cool things about trees, and so I could just talk every December. I could talk about the coolest thing I learned about trees that year. And that went on for more than 20 years. Now, I still learn cool things about trees every year, but they're getting harder and harder to explain to a general audience. So starting about 5 or 6 years ago, we just changed it to the Christmas lecture. But this year it's again a Christmas tree lecture because I got last year when I was putting the final touches on this book, volume 4B of The Art of Computer Programming. Hey, see that? Applause. Thank you. I learned something that I said, oh yeah, this is going to be a great lecture, and so I'm going to have fun tonight. I mean, it's, from a lecturer's point of view, it's always best when you have something that you love to talk about. So now, speaking of Christmas, by the way, this book makes an excellent present, and so if somebody doesn't know what to give you as a gift, why not try suggesting this one? And another thing, I have a tradition of giving away books at this lecture every year. So if you look in front on the floor, there's quite a few books. Actually, there's 3 times as many books this year because we've had 2 more years to accumulate. What happens is that my books keep coming out, in new editions, and every printing is a little bit different, and I have to check to see whether they followed it up again. And also I get books are translated, and I only need 1 copy of a translation, but they send me 2, and so on. So I have extra spare copies of books, and they're sitting here. But I have 2 rules about these books. The first rule is only 1 per person, and the second rule is you have to wait until the end of the lecture in order to touch them. So I want somebody to stay for the whole thing. Now. Okay, and I'm going to sit down now, and most of it is going to be about these 3 topics that are announced: Twintrees, Baxter Permutation, and Floorplans. And so we start with number 1 is Twintrees. You can't see the top. Whoops, I can't either. All right. Now, this is an idea goes to at the 2 guys named Dulucq and Guibert in 1996, and I have to say that it's one word. In 1996, they called it Twintrees with a space between it, and but then it turned out that 2 other guys came up with a completely different concept in 1993 that was called Twintrees. And so these guys wrote another paper in 1998 and called it twin binary trees. Well, I think I like to make it just one word, so I'm calling it Twintrees. And the topic is in volume 4B in 2 main exercises. There's one on page 27 about Baxter Permutations, and there's this one on page 172. And if I zoom in here on this, you'd see that it actually talks about can you see? Wait a minute. Here we go. I got floor plans, but I also have Twintree. Okay, but here. You see, I still spell it with 2 words there, and the 3rd printing is going to change that. But what are they? Well, you might guess that they're trees. It's a pair of binary trees. A binary tree is a tree in which every node has either no children or it has potentially two children, a left child and a right child, and both of them have nodes 1 through n. When you look at the tree in symmetric order, and I'll tell you what symmetric order is in a minute. And the easiest thing is for me to just give you an example of a twin tree, because a twin tree is a pair of binary trees. And so, well, it's Christmas time, so I'm going to draw the first one in green, and so I have a node here, number 4, and then here's 2, and here's 1, 3, 6, 5. This is going to be a binary tree with 8 nodes in it, and symmetric order. So this is in symmetric order. Symmetric order, you take the left subtree first and do it in symmetric order. Then you take the root. Then you do the right subtree in symmetric order. So it's just reading it from left to right. It goes 1, 2, 3, 4, 5, 6, 7, 8, and then well, there's 2 of them. So the other one is this 5, 8, 7, 6. I've got to do something over here. Let's go all the way to 1, 3, 2, 4. So this is an example of a twin tree data structure. And the important concept is that node K has a right child, let's say, in exactly one of the 2 trees. And the same thing for a left child in exactly one of the trees. So this is when K is between 1 and n but not equal to n, and this is when K is between 1 and n but not equal to 1, because one never has a left child. 1 is the first thing in symmetric order, so it can't have a left child. Well, now, so let me just show the left and right children here. So let's see. I zoom out a little bit. So if I look at 1, 2, 3, 4, 5, 6, 7, 8, and I write down there the left and right children, this is going to be left and this is going to be right, and the root of the tree is 4, and the children of 4 are 2 and 6 left. Okay, the children of 2 are 1 and 3. Children of 6 are 5 and 7, and children of 7 is 8 has 7 has a right child. Now, if I go to the red tree, its root is 5. It's got the left 1 and right is 8. 8 it has left is 7. 7 has left is 6. 1 has right of 3. 3, 2, 4. Okay, so here you see that this is inside a computer. I can share the red and the green stuff as long as I have a way to tell which is red and which is green. They don't interfere with each other. It's exactly, K equals 4. That 4 is going to have a right child in one of the trees, but not in 2. So not going to be any clashes. All right. So now you might think that this is a really unusual construction. I mean, here we have maybe you have to search until you find such a magical thing that has this great property. But in fact, there are more than 10,000 twin trees of order 8. And in order to verify that, let's just generate a random one right now. So I'm going to need the help of the people in the front row. So I'm going to have a random permutation, and actually, okay. So I'm going to ask you. There's going to be a 2 in here. It's going to be either on the right or the left of 1. Which should I do? To the right? Oh, I just wonder if you were conservative or liberal. All right. Now, the 3 has to go in here somewhere. You can be at the left or in the middle or the right. Which should I do? You want to what? I sorry. Just say middle, left, or right. Middle. Yeah, okay, I shouldn't have said anything about conservative and stuff like that. Okay, now, all right. Number 4, there's 4 places to put it. What do you think? Okay. Now, this isn't looking random enough. I'm going to ask for the next one because
1 and 3.
1 and 3. Okay. Now we got 3 more to go. So.
Right again.
All right. And
To the left of 1.
are you ready? To the left of 1? So we have extremists here. Now I'm going to ask.
Let's put in between 2 and 4.
What?
Between 2 and 4.
Between 2 and 4. Okay, that's 8. Okay. So anyway, now I'm going to show you one of my favorite algorithms of all time. For more than 50 years is the algorithm called binary tree insertion, and you take a permutation and you write down the first element and you put that in the root. Then you look at the next one, and if it's less than the root, you go to the left. So 1 goes here. The next one is 5. Well, 5 is also less than 7, but it's bigger than 1. So 3 is less than 7. It's going to go in this left subtree somewhere. It's bigger than 1, less than 5. So 3 comes in here. 2. Wow. 1. It's going like this. 8. Here we go. And 4. So 8 is less than 7, or less than 5. So here's 4, and 6 is going to stick in here. All right. So in my well, let me do the red ones though, because so anyway, you can get any binary tree from some permutation, but now let's take the same permutation and do it right to left. So we put the 6 here. And then we insert the 4, so the 4 has to go left of the 6. And then the 8 has to go to the right, and the 2 has to go to the left. The 3 is less than 6, is less than 4. 5 is less than 6, bigger than 4. 1 sticks all the way here, and 7 is going to fit here. Okay, so now we got this this thing, and I'm hoping I did it right because it's supposed to give us a twin tree. So it's 1, 2, 3, 4, 5, 6, 7, 8. Forget this. And 7 is the root here. 7 has 1 and 8. 1 has 5 to the right. 5 has 3 and 6. 3 has 2 and 4. And 6 is the root of this guy, and it's got 4 and 8. It's looking good so far. 4 has 2 and 3, and 2 has 1. 2 has 3, sorry, 4 has 2 and 5. Yeah. So, and of course, these are all, okay. So now it worked. So we get lots and lots. Any permutation is going to give you a twin tree, but there's going to be, a lot of times two different permutations are going to give you the same twin tree, and we'll have to worry about that. But why does it always work? Well, the reason is that L of k is empty if and only if k minus 1 was inserted into this thing before k, and r of k. You see why this is? I mean, let's take 4 for example. So if 3 came before 4, then I couldn't possibly have a left child on 4 because 4 would have to be somehow. There's nothing between 3 and 4, but so it would have to go. And this is the same, but with k plus 1 inserted before k. So if we reverse the permutation, k minus 1 is going to go on the other side, and so they can't both be L, all right? They can't both be R, and there's no room. They have to fill up also because there's just enough total room. And by the way, this is also if I plug in k plus 1 for k here, this is also the same as saying rk minus 1 is unequal to null, and this one is saying L of k plus 1 is unequal null. So if you look at any of these diagrams and you look at the things that are diagonally opposite, there's always going to be, this is green, red, red, green, green, red, red, green, green, red, red, green. Well, this was too uniform, but that always happens, that you have one of them is green and one of them is red. If I look at that, okay. So now this is something that this tree insertion algorithm has been something that I was playing with from the middle '60s, and I've used it in a zillion computer programs, but I never. It took 50 years before I understood that it also gave me twin trees at the same time. All right, now my plan is I'm talking about 3 things: twin trees, Baxter permutations, and floor plan. And so I'm going to tell you, about each of the 3 at first, and they're going to set. And in fact, they arose completely different by completely different groups of people. They didn't know what they were. They didn't know about each other at first, and then I'm going to explain why there's amazing connection between all these 3 things. So next then is Baxter permutation. And this is Glen Baxter, 1964, and he was studying continuous functions, fixed points of continuous functions. But during the course of his study, he came up with some permutations that had peculiar properties, and the more he looked at them, and other people started looking at them, the more properties they were discovering. I think I first heard about Baxter permutations when Giancarlo Rota gave a lecture to the math department in the early '70s. So what are they? We have a permutation of the numbers 1 to n, of the numbers 1 to n, and then I take the inverse permutation. So Q. The idea is that the inverse permutation tells you, like QK equals L if and only if PL equals K. It tells it tells me where does K appear in the permutation, and inside a computer, if we want to, somebody tells us what P is, we quickly compute it by saying Q of P of L equals L. For all L. So you're given P, and then you immediately can calculate Q inside. Anyway, let's do it for this random permutation that we came up with a minute ago. So that was 5, 7, 1, 5, 3, 2, 8, 4, 6. That's P. And so Q is, 1 appear in position 2. Let's do the 7. So 7, I get a 1, 1 gets a 2, 5 gets a 3, 3 gets a 4, 2 gets a 5, 8 gets a 6, 4 gets a 7, and 8 gets, no, what did I do wrong? 6 gets an 8. That's true, 6 gets an 8, 8 and 6 are switched. Okay, that's fine. So I told you what permutations are, but I haven't told you what Baxter permutations are. So Baxter permutation has no bad cases, no bad configurations, where the first kind of a bad configuration is formally it says QK is less than L, PL is greater than K, PL plus 1. This looks very scary, but I'm going to explain why it's actually not scary at all. But you look it up in Wikipedia and it'll tell you this definition. And then there's a second case which is bad, and that is QK plus 1 less than L, PL less than K, PL plus 1 is greater than K, and QK is greater than L. Now, so you got a question? Yeah.
How did you generate Q again? Yeah.
How did I generate Q?
Yeah.
L equals 1 up to N. So I looked at P1 and it's equal to 7, so I said Q7 equal to 1.
Got it.
All right. Yeah. Thanks for asking. Yeah. Please interrupt if I. Okay. So I said I said Q1 equal to 2, Q5 equal to 3, Q6 equal to 8. Now, but QK less than L says that and QK plus 1 is greater than L. So here's, let's say PL and PL plus 1 are sitting here. Then QK is K is somewhere off on the left. K plus 1 is somewhere off on the right. If I'm looking at positions L and L plus 1 of this permutation, but here QK plus 1 is less than L. That means K plus 1 is appearing here, and K is appearing on this side. But now PL is some number that's bigger than K, and PL plus 1 is some number less than K. And and this is a less than K. And so if we consider a particular number K, this has to work for any K and L. I don't want to have any badness here. It says that we can take for a fixed number K. Let's say K equals 4. The numbers that are bigger than 4 let's call big, and the numbers that are less than 4 let's call small. It says I can't have a big followed by a small. As L varies, that means I have a big one followed by a small between K and K plus 1. If K appears before K, so if 4 appears before 5, I can't have I can't have a big guy and then a small guy so the the other case is similar. If I have k plus 1 occurring before k, then I look at all the numbers between the two, and I can't have a small followed by a big. So the smallest possible non-Baxter permutation is actually one of the most famous permutations of all is 3, 1, 4, 2. You see, take k equal to 2, and so 1 is small and 4 is big. So I have, I have a small followed by a big here. Are you with me? Now, why is this such a famous permutation? Well, I call it the pi mutation because, everybody knows that pi is 3.142. But for years, I've been working with permutations, and I've done countless problems where I have a conjecture about the way permutations work, and if the conjecture is false, it almost always fails at the pi mutation. So there's something about this that makes it important. So the other thing is the inverse of the pi mutation, which is also the left to right reversal of it. That fails the first case. Here 2 occurs before 3. And we have a big number followed by a little number. Okay. So if n equals 4, these are the only 2 non-Baxter permutations. And there's 24, 4 factorial is 24, so there's 24, so n equals 4. Then we have 22 Baxter permutations. And for 3, 2, and 1, they're all fine. And we get to 5, there's 92 out of 120. And 6 was 422, 7 was 2074, and 8 is 10,754. Now, 8 factorial is about 40,000. So we got a chance of something like 1 in 4 that this random permutation that you guys came up with is Baxter. How are we going to check to see whether 71532846 is Baxter? Is it bad or not? Well, we just have to check k and k plus 1 and see what's big and small between. So 1 and 2 is never a problem because everything is, there's no small numbers between 1 and nothing less than 1. So 1 and 2 is no problem. But 2 and 3, there's nothing between them. Between 3 and 4, though, we've got 2 is small and 8 is big, and that's bad. It looks like 3, 1, 4, 2. No, it's not. No, this is fine. This is fine. This is 3 followed by 4, so no problem. 4, 5. Now we've got to have 2 and 3 are small, and 8 is big, so that's no good. So here's a counterexample where k is 4, k plus 1, and we have a small followed by large. That's the well, it's not a Baxter permutation, but we could go on 5 to 6. It seems the small guys are 2, 3, 4, and the big is 8. So there's a mixture of small and large. So it's failing on that one too. So this is, okay. But anyway, a lot of permutations are Baxter, as you can see from these counts, and it's not too hard to check a given one by just by going hopping from 1 to 2 to 3 to 4 or 5. For each time you hop, you look at the things between that and you see if the bad and little guys are in the right order or not. Now, one thing we can see in order to get an idea is if I have a Baxter permutation, I could flip it left to right, and I get another Baxter permutation. The reason is sort of that rule. The first rule slips into the second rule. Another thing is I can take if I have a Baxter permutation and I take its inverse. Again, I get a Baxter permutation because we sort of switch the Q's and P's around. But you can also put one next to each other. So suppose I have a Baxter permutation of 1 to m here. This is some Baxter permutation, and here I have another Baxter permutation of m plus 1 through n. So these are numbers 1 to m in some order, but they qualify as Baxter. And here it's the same thing except I added m to each of them. So I got I took another Baxter permutation, but promoted every number, make it bigger than m. This is going to be fine. Why? Because I go from 1 to 2 to 3 to 4 and so on, and I don't get any bad cases here. And then I jump from m to m plus 1. Well, all of the small guys are going to be all going to come first, and the big guys later between m and m plus 1. And then once I'm up into this half, and again I jump m plus 2 and so on, and I never get any bad situations again. So this is I get a Baxter permutation by sort of juxtaposing. I could also do it this way. I could put the m plus 1 to n at the left and 1 to m at the right, and again it'll jump around, but it'll work out fine. So anyway, you can see why there's a variety of Baxter permutations. And now it's time for topic 3. Topic 3 is floor plan. And this is something that is a decomposition of rectangle into rectangle into subrectangles. Okay, so and now I guess I might as well give you an example. So right off, so I'll take this rectangle here, and I'm going to subdivide it. Give you a minute to write some coordinates here: V3, V4, V5, and H0, H1, H2, H3. H4, H5, H6. So this is a 5 by 6 grid, and I'm going to divide it into subrectangles, and this one goes down to H3, and then I'm going to put one here, and I'm going to carry this over on V3. Okay. I want to. I could have prepared a slide here, but I didn't want to go too fast. You see, so G and that. Okay, so here. So I'm going to call this A, B, C. The subrectangles are called rooms. So I got 10 rooms here: C, D, E, F, G, H, I, J. And the line segments that are the so rectangle is a room, and the segments it's called a bound. So every room has 4 segments that bound it on the top, left, right, bottom. And so I've got, in this case, I've got a segment H0, I've got H1, H2, H3, H4, H5, and H6, and I've got vertical segments also. I used a V so I remember it's vertical. This is actually supposed to be just one straight line, and so this as you can imagine, concept very important in layout of VLSI. Making silicon chips, because the rooms correspond to modules or gates of a circuit, and the bounds correspond to channel. So where electrical so now the I should mention that in this decomposition of rectangles, we always have the tatami condition, which means that no four rectangles have the same corner point. In Japan, they have this wonderful age-old custom of covering their floor with tatami mats, and the rule is you don't have ever a situation where something like this would be bad, okay? Because there are four. This corner would have four tatami mats touching the same point. So anyway, that's a kind of a degenerate thing, and now the interesting thing, the important thing is when we discuss what does it mean for two different floor plans to be the same? Because there's an equivalence. There's an equivalence between floor plans, which means that it's going to give you the same circuit. For example, if you make a chip out of it. So if I can actually draw that exact same floor plan, but it'll look different if I put the bounds in different order. So here I'm going to do V0, V2, V1, V3, V4, V5, and in the horizontal I'm going to go H0, H1, H3, H5, H2, H4, H6, and I'm going to draw the exact same floor plan. So A went from H0 to H3 and V0 to V1, so it's going to be H0 to H3 and V0 to V1. So this is going to be A now. B goes across on H1. C is between V1 and V3, which is just this little thing here. So C is between H1 and H3. G goes H1 to H2. So G is now going here. Okay. And so on. So I'm going to get D between H3 and H5, and then E is down here. F is this big guy. H and J, and I claim that this is the same diagram because each rectangle has the same boundaries. Now, it needs some notation for this. So I'll say, for example, V0, right arrow A, V1. This means that V0 is at the left of A, and V1 is at the right of A. All right, and H0 is above A and above H3. And so I've got 10 rooms here, and so I'm going to have, there's 40 different relations between these things. But the idea that two floor plans are equivalent if they have the same relations. In other words, if there's a one-to-one correspondence between the rooms, so like room A here corresponds to room A here, and the bound. So bound H0 corresponds to H0, H1 corresponds, H3, H2 got here, and so all of these relations are preserved between these two things. I put the labels on just so you can see what matches between the two. But I could have made the labels blank, and I would say this floor plan is equivalent to this floor plan because there's a one-to-one correspondence between the rooms and the bound. All right, now you got questions on this?
So if you represented the two floor plans...
Please speak very loudly. I forgot to wear my hearing aid.
Yeah, so if you represented the two floor plans as graphs, would they look the exact same?
If I represent as graphs, then what?
Yeah, so the rooms are nodes, and then if they share a bound, it's an edge. So would the graphs be isomorphic?
The graphs are, if you label the... Yeah, but you have to consider that the different kinds of arcs. There's the horizontal arc and a vertical arc, and so the graphs are isomorphic, but you have to distinguish a horizontal. If I didn't distinguish horizontal from vertical, then it would be a different concept. Now, you talked about representation, and of course one of the things we want to do is represent this in a computer in some way. And we'd like to have a representation that equivalent floor plans look the same inside the computer. Easy to tell that this one equals that one. So now I want to explain to you how we can get a canonical form that I can take any floor plan and I can draw I can draw it in a certain way so that both of these would turn out to have the same result. So there are 10 rooms, and for this canonical form, I'm going to use this kind of paper, and I'm going to give myself 10 by 10 area to work with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that you can see what I'm doing. I guess I got 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm gonna redraw this floor plan in a canonical way that both of these are going to end up the same. So I might as well just use this one to start with. And now you notice that inside a floor plan, I said we got the tatami condition. So there's only 4 kinds of junctions that we can have. A junction can look like this, it can look like this, or it can look like this, or it can look like that. But at the corners we only have 2. But otherwise, these are all junctions. And so I start at the upper left-hand corner, and I put it here, and then I look at the lower part of that room, and I see that it ends with a upside down T junction for A. So it's up in the lower right hand corner. It's an A, which means that the boundary here, the right bound is this vertical bound V1, and then there's going to be a neighbor on the other side. And the fundamental idea, it is called flattening. And so I'm going to take A here, and I'm going to flatten it by moving this bound all the way to the left and smashing A so that its width has gone down to 0. And then so this B and this line is going to extend over. It's going to I'm not going to redraw the whole thing, but after I flatten A, B is going to extend all the way to the left, and C is going to extend all the way to that. But D and F and all these other guys are still going to be the way they were. So in other words, just I smash A by moving it all here. Now I've got 9 rooms left, and I'm going to find a canonical form of these 9 rooms. And later on, put A back in again. So in a way, that means I want to. Later on, I'm going to put a line here, and what I'm doing is I'm flattening A. So I'm sort of setting V1 to V0 because V1 has moved over to V0. So I'm going to call this V1 here. This is V0. Now, so now I'm left with B, and what kind of a junction is at the other side of B? Well, B has has this kind of a junction. In its upper right-hand corner, and so I'm going to flatten B upwards instead of left-right. And flattening B upwards is easy in this case because I just remove it from the diagram. So I'm going to have B flattened here, and I'm going to change H1 to H0 because I'm moving H1 up, flattening out B, and I'm going to put a line below it, B, because later on, after I get the canonical form, I'm going to put B back in again, unflattening the guy. Okay, well, C also has a junction like this after it, and it turns out H3. Let's put H1 here, and H3 is going to go here. But it's going to go here. Excuse me. Forget that. I'm not going to put any H here. I'm going to put an H here, and then C is here with H3 goes to sort of H1 when I flatten C, and now what does this look like after I flatten C? Well, D and F have moved up, so now the current state is I got D sitting here, and F, and G, and D is another one that has the same business here. So H5 is going to go to H3, and so I'm going to put D here, and H5 is going to be underneath it. At this point, we get a break in the action, and E is after I slid this up, then E came up here, and E goes all the way down to the bottom and has the upside down T junction again, and so that's going to be a V2 to V1. So I put an E here, and I put a V, and I put a line to the right like I did with the A, and I put V2 over here. So anyway, this is a systematic construction, and if I were doing that not on this diagram, but if I was doing it on this diagram, I would be doing exactly the same thing, because they're isomorphic according to according to the rule, the right bound of A. The same junctions are there, and I just move everything up. So what's going to happen is I'm going to get GHIJ, and that's and F. I might as well write the whole thing down because this is going on the internet. G H I don't pay for errors in this though. And J has actually a corner, but this is going to say V3 to V2. So F is going to be here and going to be V3, and then this is going to be an H and a V, and this is going to be both H and V. So this will say A, H2, H5, and this is going to be H2 here, and H, I'm going to get H4 here, and I is on the right. I'm going to get a V4, and here I'm going to get V5 and V and H6. Okay, so this is V5, this is V6, H5, and this is H4. Now I know where the bounds are in this thing, and so now I just have to draw the I have to draw the diagram. So I know that A goes from V0 to V1 in one direction, and H0 to H3 in the other direction. So A is now here, and B is going to take over this whole space, and so on and so on. Okay, well I've got it. I've got it here. So that's what I just constructed by, and this is I say canonical form for this for that floor plan. Now, but we can do the same thing. We can, by the way, it's not a coincidence that it came out in alphabetical order, A, B, C, D. But I had to choose some arbitrary names for these rooms, and so so that's the way I picked them. I could have called them anything, but I chose to put them in, so that this one, take any floor plan. And convert canonical form, look at the diagonal, and name the rooms 1 to n or alphabetically, whichever you want. Now, but that same procedure that we just used for canonical form, I could make another canonical form where I interchange bottom and top. So instead of starting at the upper left corner, I could start at the lower left corner. And instead of looking at the junction here, I could look at the junction opposite. And so if we do that same procedure again, but we go bottom to top instead of top to bottom, then we get this pattern, which is it's the same it's that same floor plan, but it's canonical, but it's the anti-canonical form of so we get two canonical forms. One has a diagonal which goes in strictly increasing order, and the other is the anti-diagonal. Both of them are permutations, and well, now it's time to say, well, why? What does this have to do with Twintrees and Baxter permutation? Well, the second answer is the easiest to say. This is a Baxter permutation, E to D, And it's if and only if. In other words, every floor plan, when you put it into canonical form, with the diagonal one to n and the anti-diagonal a permutation of one to n, that permutation is a Baxter permutation, and every Baxter permutation gives you a floor plan. So the number of floor plans with 4 rooms is 22. The number of Baxter permutations, the connection with Twintrees is even nicer, and so let's take a look at the at what Twintrees we get from this permutation. So the green tree starts with E, and then comes D, so that goes here. Then comes F, which goes here. Then comes A. Then comes C, less than E, it goes here. I is bigger than E, it's bigger than F. H is less than I. J is bigger than I. G is bigger than F, less than H. B is down here. And do the other in the other order. We get the twin of the tree, and that's B. And G comes over here. J, H, I, C, here, A, F. F is here. D. That's it. D is big, less than G. Big, okay, D, E. Looks like this. Looks like you got this. Okay, now Twintrees, and I've I did this with my computer, so I'd be sure I get it right. So here are the Twintrees that correspond to that permutation, to that permutation which I claim is a Baxter permutation. And here we start to see I put dots around it. Looked at E, F, I, J. Well, it turns out E, F, I, J is exactly the rooms that are at the bottom of this diagram. You see, E, F, I, J. And so I call that H6. These are the things just above H6. Okay. D is what's just above H5. What's just above H3? A and C. Here we go. H3 is here. What about H4? That's just H. That's just H4. G is H2. B is H1. These families that we see in the twin tree are exactly what goes next to a bound. These are the, H is a channel. These are the modules that touch that channel. What?
Can you move the page down a little?
Can I move the what?
The page down. We can't see the top again.
Okay. All right. I have another idea. Let me go to. Let me go to volume 4. Okay. Well, anyway, here we got the picture. But if I go to the answer to exercise 372. No, I guess we can't see them both at the same time. But anyway, this picture is in the book. Okay, yes. So I zoom out, and we can see the whole guy. Okay, so now, as you can imagine, that like B, G, J. These are the guys touching the right thing. Those are those are in this tree. Okay. The guys less than V5. The guys who are less than V4, that's just I. I'm sorry, B, G, J, H and I. So this is V. No, this is V5. This is V4, and so on. V3, all the V's appear here. But now on this side, I got G and C. Well, what's that? That's below H1. So A and B are the things below H0. So the idea is for each of the bounds, in your circuit, you want to know what are the modules touching that channel on top and touching the channel underneath, and they occur in the twin tree as a sequence of left links or right links. So this beautiful representation inside the computer for the floor plan. Now I've got I put some programs online because this amounts to a wonderful trio of bijections, one-to-one correspondences between floor plans, Twintrees, and Baxter Permutation, because you give me a Baxter Permutation, I can tell you what the floor plan is. You give me a floor plan, I can tell you what the twin tree are. You give me a twin tree, I can tell you what's the unique Baxter Permutation that generates it. And those are all, and all of those algorithms are linear time. The length of the permutation. They all take order n steps to go from one to the next in the sequence, and I've got a sequence of computer programs online that implement this, and I forgot to bring the programs copies of the programs with me, but these are literate programs, which means that intended to be read by people, and let me zoom in here so you can see a sample run of the program. By the way, thanks for focusing. If somebody's interested, they could take my programs and convert it into an app, which will make all of this wonderful graphic interface and flatten floor plans and enjoy yourself. But anyway, this is what my program gives you. So I type in a permutation, and this happens to be the permutation of the example. But the letters are converted to numbers, so this is E, D, F, A, C, and so on. J is 10, and so this was the input, and the output comes out and says, well, room number 1 goes from at the left is Y. I guess this is top, bottom, left, right, top, bottom, left, right for each room. And it cranks out the floor plan that corresponds to this Baxter permutation. And if you give it a permutation that's not Baxter, it sneers at you and says, "Too bad, you lose. It's not Baxter." Now, I can feed this floor plan to another program called Floor Plan to Twintree. And this was the input, and so it read the specs for 10 rooms and 7 horizontal bounds, 6 vertical bounds, and so here's the twin trees that comes out. So the first tree is rooted at 5, and it says 5 goes 4 at the left, 6 to the right. So these are the left and right links in the tree, and then I have another form of this floor plan to twin tree, which is called the TT form, which produces output in another form. This is a form where you first show the roots, and then you give the left and right for the two different trees. This is the form that's the input to my third program, which is called Twin Tree to Baxter. And if I feed this to and feed this one, and then I feed that to Twin Tree to Baxter, I get back, of course, the one I started with. So those programs are all online on my homepage, and I have. I guess I should say a couple of things about it. Before I finish, but I'm almost done. The first thing is this Baxter to floor plan. The ideas in there are due to Ackerman, Barakay, and Pinter in 2006. If you look at the code for this algorithm, I mentioned, I wrote this when I was learning it, but this algorithm is almost too good to be true. So I recommend reading the algorithm, not just using them. The floor plan to twin tree is due to people named Yao, Chen, and Graham. And by the way, this is our friend Ron Graham, and this is 2003. And the program has several phases, and one of them is called the cool phase. And again, it's okay. And the twin tree to Baxter is an algorithm that's based on the guys who invented twin trees, Dulucq and Guibert, 1996. And this, we get to a part of that program which is called a stunning construction, which is in lemma 4 of their paper. So anyway, these algorithms I believe are fun to read. The final thing I want to explain is that explains the whole. The main connection there is I'm going to draw just 4 little diagrams for junction. I have a T junction, this junction, this junction, and this junction, and say, suppose I have a room R in this position in the floor plan. Then L of R is here, R of R is here. In other words, the right branch below R, and green L of R is here, and green R of R is here. So this is the magical, the amazing connection between all of these things. Here we have the links of the twin trees. Here we have the junctions in the floor plan. All right. Well, I'm 10 minutes over. I was expecting to be 20 minutes over, so I'm glad I didn't. So thanks for listening, and I'm ready for questions.